recall that copper is not a ferromagnetic material, right? We saw that. But why does this happen? See, here you have a copper wire and you have a magnet. They're not supposed to either attract nor repel because it's not a ferromagnetic material. So why is that it is moving with this much of speed? Why is that happening? Well, to understand that, we have to go back to this. Do you guys remember this? We spoke of non-contact force and we get an idea of field from this. And field is seen gravitational field, electrical field, and magnetic field. So for anything related to gravity, we need to talk in terms of mass. Anything related to electric, we need to talk in terms of charge. Anything related to magnetic, we need to talk in terms of moving charges. So in this picture, we can see clearly that this particular setup has a current supply. Okay, so let me show it to you how the conventional current moves. So you have the current going in this way, you go this way, okay, through the copper wires, there are n number of it, and to the negative end, right? That's how the charges are moving. So what happens? Well, these are nothing but charges. They're moving charges, is it not? So what does moving charges produce? Magnetic field, right? So moving charges produces magnetic field. So there is a magnet. What happens with magnet in presence of another magnet? Either they will get attracted, if not repelled. Is it not? Right? So to summarize, what did we see? Current has moving charges. Moving charges produces, let me change the color. Current is nothing but is moving charges. It produces magnetic field. So moving charges also is made up of electrons. I mean, majority it's electrons only, but I'm just telling. So majority, actually not majority, it's by default moving charges is nothing but your electrons. Electrons are bound in the material, right? That is, they can't just move out of the wire. So if the electrons which are producing magnetic field in presence of another magnet, what will happen? The electrons will get pushed or pulled, is it not? But one more thing is they're bound to the material, means they can't just come out of the material. It's not that easy. So what will happen? The electrons want to move and they're tied to the material. So what happens? The wire itself moves. Make sense? Let me repeat. You have charges flowing around, right? In this wire. So it produces north and south pole. We don't know which, as of now, we don't know which produces what, which side produces north and which side is south, and where is north and where is south, we don't know. But we know that there is charge flowing and produces magnetic field. So in presence of another magnetic field, either it pushes or pulls. And somehow I made the setup so that there's a very high speed rotation, right? It's rotating. Why? Because the charges are moving around over here, which in turn produces magnetic field, and the magnetic field will push another magnetic field or get pulled, right? And one more thing is this electrons that is producing the magnetic field is bound to the material. That is, it is part of the material itself. So since the electrons are getting pushed and pulled and it is bound to the material, it will also pull and push the wire itself. As a whole, it will start moving. And that's why we see that the wire is moving. Right? Make sense? So electron is the cause of the current. Electron is also cause of the magnetic field. So they'll get pushed and pulled, but they cannot go out of the material. So they have to push the material so that they also get away from the magnetic field and some towards the magnetic field. Okay, got it? So and thus we see movement of wire. So all this is well and good, but there's a big question. Which side of this wire, where is my north and where is the south in this copper wire? You know, yes, it makes sense that, okay, I have a magnet over here, I have one more magnetic setup over here, so that's why we see a movement. It makes sense. When you get two magnets near each other, they either pull or push. So we kind of see a force, right? That's the whole idea of this field and non-contact force and all of that. But what direction is the north over there? Where is the north over there? Where is the south over there? What is the shape and direction of a magnetic field by a straight wire? See, in a ring-shaped magnet, the magnetic field was different. You saw that practically. In a bar magnet too, we saw the magnetic field was different, right? In a horseshoe magnet, I don't have that. Actually, I can get it. I think I'll get it and try to put the magnetic field produced by horseshoe magnet as well. It'll be something like this, it's going like this. And so point is, it will be structured differently. The magnetic field will be structured differently over here, here, and here. So obviously here too, it will have its own structure to look at. So the next big question is, what is the structure? What is the structure produced by a straight wire? So that's what we'll try to understand in the next set of videos.